All right, good morning. So last lecture we ended at a place where we started describing the algorithm for computing just the more than one eigenvalues, right? So this algorithm is going to generalize to an algorithm that can compute the leading n number of eigenvalues, no matter what n is. So let me. Yeah, so it is also included in the first homework. If you have you looked at the homework assignment yet? Yeah. There is a typo. Where? Oh, okay. 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 I'll take a look and fix that. Yeah. Thanks for telling me. All right. So today we are going to demonstrate this algorithm not on the homework problem but on a simpler system so that you can generalize to the homework problem. We'll also look at error analysis to the algorithm and figure out actually how many iterations we will need to get the error of the resulted eigenvalues to the required precision.
That reminds me, I had a question about the homework in that how much do you want things just written on hand, or would you prefer like just Python scripts? Like to do the error analysis and stuff like that. Like I guess it depends on how many iterations you go and all that.
Yeah, I like it to actually type it out if possible, right? And the Python script should also be submitted, but like I don't want the submission to be just a pure Python code.
Okay. Okay.
Yeah. Okay.
Then I guess
Yeah, because some of the math formulas are a lot easier to write down than put it in a Python code, right?
Okay.
Yeah. Okay, so let me first recap what the algorithm is like. So the algorithm starts with a matrix and will later generalize to a nonlinear system. So instead of randomize one initial vector, we randomize two initial vectors. And we multiply both initial vectors with the matrix X. And the crucial part is what happens after the matrix vector multiplication. Okay, we take the first vector, normalize it. So what we do to the first vector is actually exactly the same as our previous algorithm for computing a single eigenvalue and eigenvector, assuming we renormalize after every multiplication, right? So last lecture we demonstrated that it's okay to renormalize at the very end of the k multiplications, or it is equivalent that you renormalize occasionally, right? After a few iterations, you make the norm of the vector to be 1. So this is basically equivalent to renormalizing for after every iteration. So basically divide the vector by its norm. So what's really different is what we do to the second vector. After we multiply a with x1, before we normalize it, we actually also make it orthogonal to the first vector. So this is the subtraction sign. The R01 is computed such that it is a projection. Okay, the magnitude of the subtraction is scaled in such a way that after the subtraction, the new vector is actually orthogonal to the x0. And then we normalize it. Okay, so this is what we do to the second vector. And in a generalization to multiple vectors, you also have a third vector, and you have to somehow make the third vector orthogonal to both the first two vectors. Okay, so we have also seen that this procedure, these three equations, is equivalent to constructing a 2x2 upper triangular matrix with 3 elements. And the 3 elements are these 3, right? R00 is the norm of the first, R00 is this is actually R00. Yes, we already said it here. and R01 is the normalization, is the orthogonalization constant, and R11 is the normalization constant of the second vector. Okay, so this is equivalent of multiplying the vector and use the upper triangular matrix to make the new vectors orthonormal. Okay, so then basically we get x1 two orthonormal vectors, and we can proceed again, right? Multiplying A again with x1 and use another 2x2 upper triangular matrix to make the new product orthonormal again. So after k iterations, this becomes the formula, right? A to the kth power times x0 would now becomes a new set of vectors after the k iterations. We call it xk, right? Multiplied with a number of upper triangular matrices. And let's see. Okay. So every time you multiply, right, you get a new upper triangular matrix on the right hand side. So actually let me denote it 0 to k, right? So that basically this is the transformation matrix from x0 to xk, right? So let me actually denote all of these 0 to k. And so this is going to help you compute the product of the two leading eigenvalues. So today we are going to do two things. One is to demonstrate the algorithm in Python, and two is to analyze why this procedure is going to give you the product of the two leading eigenvalues. And in that process, we are also going to analyze how much error we get in this product. Okay. So first thing is going to Python. So this is the code we started last Wednesday. So we randomized the 4x4 matrix. We also computed two initial random vectors, and we multiplied the matrix A with the first and second second vector, and we did the normalization, the orthogonalization, and the normalization to the second vector. Right. Okay. So let me just make sure this. Oh, I think I need to import a bunch of things. Let's actually numpy import all. Okay. So now this works, and let me just demonstrate the equivalence between the few numbers we got over here and the multiplication with the upper triangular matrix. So in this case, this square root, right? Let me just copy and paste it here, is actually our R00, and the division is by R00. This dot product here, let me also paste it over here, is our R01, right? And this subtraction is actually by R01. And finally, this square root is our R11, and this division is by R11. Okay. So if you print out these three numbers, R00, R01, and R11, and we get the following. And let me see, we can do the equivalent thing by actually computing the dot product between A and let me just put x0 and the x1 and transpose them so that we get a 4x2 matrix, and compute the QR factorization. So linear algebra.QR factorization of the matrix. Let me print that out. Okay, so here let me just both print out the r's and also x0 new and x1 new. And in this case, let me just say my q and r are equal to the QR factorization, and the print out r and the print out q. Okay, so let me just say r0. Okay, and All right, so let's take a look at the correspondence between these two procedures. The first procedure is the Gram-Schmidt orthonormalization, right? We get the three numbers R00, R01, and R11. And look at the correspondence between these three numbers and the upper triangular matrix we get through the QR factorization. Other than the minus sign, right, they are actually exactly the same. Also look at the correspondence between the two new vectors we obtained and the Q matrix we obtained. The Q matrix, if you look at these two columns, other than the minus sign, right, they are exactly the same as these two new vectors. So essentially, the QR factorization is actually a pretty good way of doing this orthonormalization procedure, right? So okay, so let's actually use the QR factorization to proceed with our iterations. So basically, keep multiplying the new vectors with the matrix A and keep doing the QR factorization. And the Q is essentially the new vectors you want to use to multiply with the matrix A.
So in the linouch.qr function, is it just in the background doing exactly the same math you did on top, or is there like a different thing?
Good question. There is a different algorithm.
Okay.
Yes.
Faster.
So it's yes, the algorithm is not necessarily faster, but a little bit more stable. More stable means that if you have a small error, like small numerical error in one of these ingredients, the error would actually amplify less than in the Gram-Schmidt orthonormalization.
Okay.
Yeah. All right. So let's keep the procedure going on over here, right? So we are going to start with Q. Let's just copy this. This is the beginning of the algorithm we started, and we are going to have a collection of R's. History, let's say, start with the empty. Actually, let's just put the initial R into this history, right? And then let's say go for 100 iterations. And over the 100 iterations, I'm going to be doing QR factorization, but of the same thing, but it's no longer the transpose of x0 and x1, but instead we are going to use the Q from the previous iteration, right, to fit into the new thing. And R history, we are going to append with the new R. Okay, and let's actually look at what the so let's look at two things. One is the eigenvalues of the matrix A, particularly the product of the two largest eigenvalues. So let's print the linear algebra dot eigenvalue on the matrix A. Actually, I only want the eigenvalues. And the second thing is really the product of the determinant of the matrices R, which is of course the determinant of the product, right? Okay, so what we'll do is see what's the best way to do this. We'll just also print out actually let's actually print out so R, the diagonal component of R for R in R history, and the product of that. The product of that over the first dimension, which is going to basically multiply the 1-1 entry of all the R's and also the 2-2 entry of all the R's. And let's take a look at what it does. Okay, so this is what we have. So let's first take a look at the matrix and identify the two largest eigenvalues. The two largest eigenvalues, it looks like, okay, the two largest eigenvalues means the two that has the largest magnitude, right? And it turns out one of them is this one, and the second one, unfortunately, is a pair of complex eigenvalues. So this algorithm, because it actually depends, just like the previous one, the gap, right, between the first two, between the second and the third eigenvalues, these wouldn't really work in the sense that it won't be able to compute the actual eigenvalue. But it'll so we'll see later. It'll capture the magnitude of the second eigenvalue, but it won't be able to compute the eigenvalue itself. So maybe we should do another randomization of the matrix A and do it again to see if we can get two large. Yeah, okay. So this time we get a bunch of real eigenvalues, and the two largest in magnitude is the 2.1 and the 0.65, right? Okay. And then, if you look at the product of the 1-1 entry, it gives you a very large number. But that very large number is basically the product of the R00s, and the second one is the product of the R11s. Okay, so let's first figure out what is the product of the R00s. It is actually the product of the magnitude of the first vector we got, right? Except for there might be a sign difference. Okay, so that's why there is a negative sign over here. And just like in our previous algorithm, this is going to be an approximation to the kth power of the largest eigenvalue in magnitude. So this number without the minus sign should be roughly the largest eigenvalue's magnitude to the 100th power, which is actually 101th power, because we did like 101 times these matrix multiplications. Okay, so let's actually see if that's the case. So if we take the absolute value of these and take the power of 1 divided by 101, and let's see if we get the right thing. Okay, so we did get these two numbers, right? One is actually up to 3 digits is the largest eigenvalue in magnitude, and the second one, again, up to 3 digits is the second largest eigenvalue. Why is it 101? Let's just, for example, take a look at the largest eigenvalue, right? The largest eigenvalue, basically, so once you multiply, okay, so let's say just how many r's are there in this. So let's print length of R history. It's 101, right? So basically the matrix has been the first vector has been normalized for 101 times, right? So this the product taken to 1 over 101 power is really on average a geometric average, right, of how big that entry is. All right. Okay, can you say again?
Yeah, like if it was size of the vector was 100, but then I realized that the second line you already initialized the R, right? You look in your script.
Yeah.
The second line already has an R, so it was.
Yeah, it already has an R. That's coming from the very first multiplication, right? Okay. Okay. So this is demonstration of how the algorithm works, and we still haven't really looked into why this algorithm works. So let's do a little bit of mathematics to figure out why the algorithm actually works. All right, so let's actually make a new slide and show it over here. So we are essentially taking x0 to be a random n by 2 matrix, right? Or a collection of 2 random column vectors. And we are essentially multiplying a to the kth power times x0, multiplying it again and again. And we computed a QR factorization along every step, right? But the end product is actually equivalent to doing one QR factorization at the end. So this is equivalent to xk multiplied with k different upper triangular matrices. And if you look into the matrix algebra carefully, you're going to see that the product of 2 upper triangular matrices is still an upper triangular matrix, right? So the product of k of them is still an upper triangular matrix. So let's just call it 0 to k. It's a product. Okay, just like our previous analysis, we are going to make A equal to V, a collection of eigenvectors, times lambda, a collection of eigenvalues that forms a diagonal matrix, times V inverse. And as a result, A to the kth power is going to be equal to V times the eigenvalues to the kth power times V inverse. And this eigenvalue matrix is, we denoted lambda 1, lambda 2, lambda 3, etc. to lambda n. And we're going to order them so that the magnitude of lambda 1 is greater than the, let's say, greater or equal to the eigenvalue of lambda 2. And in this particular algorithm, we have to assume the magnitude of lambda 2 is strictly greater than the magnitude of x3, and etc. We're going to see that when the 2 magnitudes are equal, it doesn't work as well, right? But like if they are different, we are going to do an error analysis, and we'll show that the error has a contribution that comes from the gap between the second and the third eigenvalue. Okay, of course, the matrix to the kth power is going to be lambda 1 to the kth power, lambda 2 to the kth power, and lambda 3 to the kth power, etc. Now the critical step in the analysis comes from this. So let's actually represent a to the kth power times x0 as v lambda to the k v inverse times x0. And let's just denote the v inverse times x0 as y0. Okay, so y0 is basically 2 column vectors. Each column vector contains the coefficients of the corresponding eigenvector in the contribution to x0, right? So if you decompose x0 into a summation of different eigenvectors, each multiplied with a coefficient, then y0 is actually a vector of these coefficients. Okay, so then let's write y0 as, let's write it out, y0 1 1, y0 1 2, y0 2 1, y0 2 2, etc. What we're going to see is that this initial matrix is multiplied by this diagonal matrix lambda to the kth power, the entry of which has vastly different orders of magnitude, right? As long as there is a gap between lambda 2 and lambda 3, when these numbers are raised to sufficiently high power, there is a gap between the first 2 by 2 entry and the remaining entries. So if you look at this vector, this matrix multiplication, which is lambda to the kth power times y0, we can actually write it, okay, into two different blocks. The first block is lambda 1 to the kth power, lambda 2 to the kth power, times just the first 2 by 2 entries of this matrix, of this y0. Right? And then the remaining part is, we can just write it as O lambda 3 to the kth power, because these are all the entries that are multiplied with k3 to the kth power, k4 to the kth power, etc. Right? Okay. So this is super nice, because this really allows us to start using, I mean, it simplifies the whole thing, the whole iteration, from iterations that involves n by n matrices, n by 2 matrices, and 2 by 2 matrices, into an algebra that is completely 2 by 2 matrices. Right, so if you look at the left-hand side, they're like everything is now 2 by 2 matrices. Well, except for the V, except for the V. Now, if you, okay, so to get rid of the V, and which is the only remaining. 1 second. I think I missed something. So this product actually is going to be a n by 2 matrix, not a 2 by 2 matrix. So this is actually so this is actually the only first 2 rows of that matrix. The whole thing should actually have a bunch of zeros underneath, right? It's actually the first. Right, so it's the first, so this part is the first 2 columns of that product, and the remaining is the first 2 columns of the matrix lambda to the kth power multiplied by the Y matrix, and the remaining is the remaining n minus 2 columns multiplied by the remaining n minus 2 rows of the Y matrix, right? Okay. So this form also motivates the involvement of V. Okay, so then let's look at the whole thing, which is a to the kth power times x0, which is now V times lambda k times y0. And that can be written as, if we also represent the matrix V into now different columns. So this is really V, the number of, so basically V is only going to, so because this matrix only has the first 2 rows being non-zero, right? So therefore only the first 2 columns of the matrix V is going to be involved. So I'm just going to write first 2 columns times the lambda 1 to the k, lambda 2 to the k, and y11, y12, 0, plus again O lambda 3 to the kth power. All right. Okay, so this is the first critical part of this analysis, is to use this big O notation. Now the second part of this analysis, second critical step of this analysis, is to now take this formula and multiply with this transpose. So what is this formula multiplied with this transpose? It's x0 times ak transpose times ak times x0, is equal to now R 0 to K transpose times, okay, the transpose of AK with its times itself is an what matrix? If XK is an orthonormal matrix, is orthonormalized, right? Then the transpose of it multiplied with itself is going to be what? Very close. So here, for example, if we print out the dot product of Q transpose with Q, what do you think I'll get? Huh? Identity, exactly. That's a identity matrix with a round-off error of 10 to the minus 16, right? So that means the XK transpose times XA is just going to disappear from this equality. We're just going to get the product of R's transpose with R itself. Okay, and now let's use our derivation of this part, right, which is here, to rewrite this formula. With the rewrite of this formula, what we get is the left-hand side is X0 transpose AK transpose times AK times X0 is equal to, okay, first of all, the transpose of this. I'm just going to write it as a Y 1 2 to 1 2. Okay, so that's this matrix. I'm just going to call it Y 1 2 to 1 2 times the two lambdas, lambda 1 to the K, lambda 2 to the K. There is a transpose. The transpose is gone, and then the V first two columns transpose times V the first two columns, and times another lambda 1 to the K, lambda 2 to the K, and times another Y12 to 1 2. Right, so that's basically plugging the red formula into this, and another plus lambda 3 now to the 2kth power, right? Actually no, just still to the K to the kth power, because it's multiplied with itself. We are going to, yeah, so let's and then the right hand side of this is equal to R 0 to K transpose times R 0 to K. So now this is the time to compute the determinant. Okay, the determinant of the left-hand side is equal to the product of the determinants. And the only part of the determinant that actually changes with K is this part and this part. Right, as K increases, the determinant of the remaining, no matter if it's part of the V or part of the Y's, they don't change as you increase K. Right, so only the determinant of this changes as a function of K. So if you take the determinant on both sides, take determinant, what we get is some fixed quantity. Let's just call it a small a, times lambda 1 to the 2kth power, because there is a k here, lambda 2 to the 2kth power, right? The remaining are fixed, is going to be equal, of course, plus O lambda 3. I think this is, yeah, this is there is a kth power and there is a kth power here, so this I think we probably need to do a more careful analysis on this part, because this part has to be smaller than this part, right? So I think the largest term in here depending on which row you are looking at, the largest term in here actually is either lambda 3 to the kth power times lambda 1 to the kth power, or lambda 3 to the kth power times lambda 2 to the kth power. So basically, we need to do a more careful analysis to the different rows and columns of this matrix to make sure that this doesn't contaminate with the determinant. Right, so I think it turns out to be lambda 3 to the 2 kth power times lambda 1 to the kth power times lambda 2 to the kth power if you are computing the determinant. Okay, and so that's what happens on the left-hand side. On the right-hand side, there is going to be the square of the determinant of the R matrix. So the determinant of the R matrix squared. Okay, so what does that mean? That means if you can compute the determinant of the R matrix and take a power of this. So if we remove the square on both sides, right? So we get the square root of k, and then take a power of 1 over k. So take a power of 1 over k. Then we get lambda 1 times lambda 2. Right? And if we can ignore this part, that's going to be equal to the determinant of the R matrix to the 1 over kth power. So this is actually what we just did, right? So what we just did in the code is basically what we did in the code is actually computing the product of the eigenvalues independently, right? But like if you, it is actually the same as, so for example, if you for, let's say, R product is equal to a identity matrix 2 by 2 for R in R history, R prod is equal to dot with R prod and R. So basically we are multiplying R's in a series. Okay, and then you compute print the R product. Actually denote what we are computing. The product of the R's, of course, it's still an upper triangular matrix, and the two diagonal entries are actually exactly what we are looking at before we take the power, right? So let me just remove the power and then print it. So this is the first entry is the same as the product of the product of the 1-1 entries, and the 2-2 entry of the product of the matrix is the same as the product of the 2-2 entries of the matrix, right? So the determinant, which is the 1-1 entry multiplied by the 2-2 entry, is equal to the product of these two numbers. Yep.
So just kind of thinking about what you just wrote down, there should be a factor A floating around, but it seems like here that A is just the tiny a is equal to 1.
Yes, there should be a factor of A floating around. However, as we take the 1 over kth power of A, what does this converge to, right? If you take the 1 over kth power of anything, what does it converge to? It converges to 1, right? And the error analysis over here is actually the same as what we did last time. So if you take a square root of A, 1 over kth power, right? And it is actually, if you do a Taylor series expansion, this is actually approximately equal to 1 plus the natural logarithm of square root of A divided by k, and then plus order of 1 over k squared. So this is the Taylor series expansion of a exponential function, right? So as k goes bigger and bigger, 1 over k goes smaller and smaller, the error term caused by this A floating around is going to become smaller and smaller. It's going to go like 1 over k. And there is also an error term caused by this big O notation, which I think we didn't do it carefully enough. We should have basically represented. So this is correct, but like when we are multiplying this matrix with the transpose of itself, we actually need to keep track of which entry, right, in this O lambda 3 to the kth power is multiplied by lambda 1 to the kth power, which entry get multiplied with lambda 2 to the kth power when we are taking the determinant. So we should actually get that the corrupting term in the determinant is proportional to this. So at the end of the day, this is going to be, if there is a gap between lambda 3 and lambda 2, this big O notation should be much smaller than the first term. And how much smaller? It should be the gap. It should grow as the gap between lambda 2 and lambda 3 grows, to the kth power grows. So this the error due to corruption by lambda 3 should go down exponentially as you raise k, and the error due to the constant term should go down linearly as you raise k. All right. Any questions on this algorithm? Yeah. Yeah.
Like, what do you get the eigenvalue when you get the diagonal?
Yeah. Okay. So very good question, right? I didn't explain that clearly. So we get the product accurately, right? So why do we get the individual eigenvalues correctly? Okay. The reason is the following. So we have proved that this algorithm gets us the product, but also you can almost think of a byproduct of this algorithm is actually the largest eigenvalue. Why? Because when you look at the first entry of this, so if you look at just this entry, right, the 1 entry of the R matrix, it is simply a product of R0 zeros. So think of how a 2x2 upper triangular matrix multiplication works. So if you have a two matrices R11 1, R121, R221 multiplied with R112, R122, and R222, right? The product goes like this. So the first entry, you are multiplying this row with this column. What you get is R111 times R112, right? The remaining, I don't want to do the algebra. It's a bunch of stuff, right? And this one is still 0. So what is key is that the first entry of the product is actually the product of the first entries. So you can show that this algorithm, although involves 2 vectors, but if you only focus on the first vector and the 1 entry of the matrix, it degenerates, right? If you only zoom into that part, it actually is exactly the same as our previous algorithm for computing the largest eigenvalue and the largest eigenvector, right? So that means the very first component of the R matrix is actually, if you take the 1 over kth power, it actually converges to the very first eigenvalue, right? So now we have proved that the product converges the product, and the first entry converges the first entry. Therefore, the second entry must also converge to the second entry, right? So as you generalize the algorithm to actually 3 eigenvalues, 4 eigenvalues, we actually follow exactly the same logic, right? So if you derive an algorithm for computing 3 components, you're going to see that the first 2x2 block of this R matrix, now 3 by 3 R matrix, is actually exactly the same algorithm we are deriving for 2 by 2, right? And as a result, you can show that the third eigenvalue also get a convergence. All right, any additional questions?
Just I guess reorient the purpose list. This is supposed to be like a really fast algorithm, right? Calculating arbitrary number of eigenvalues, right?
This is supposed to be an algorithm that is much faster than computing the 4 eigenvalues when the matrix is very large.
Okay.
I mean, if you have a 4 by 4 matrix, this is not going to be faster, right? Because the rate of convergence, as you can see on this, it converges linearly as you increase k. So there is algorithms for computing eigenvalue for small matrices that converges exponentially, which is much faster than this, right? I mean, that's what actually Python does when you call linear algebra.ig, right? But that requires you to perform QR factorization of not an n by 2 matrix. It requires you to perform QR factorization of an n by n matrix. All right, so when n goes to very large and you only care about the first few eigenvectors, then like the QR factorization, so QR factorization of an n by 2 matrix, or of let's say an n by m matrix. Okay, so let me actually write this down. So QR factorization of n by m matrix. So when n is greater than m, costs n times m square operations. Okay, so basically what I'm saying is that when n is very large, particularly much larger than m, doing this is much cheaper than n cube operations, which is what's required for computing the QR factorization of the entire square matrix, right? So if you want to compute eigenvalue, I mean, so if you want to use the exponentially converging algorithm for computing eigenvalues, you have to do this repeatedly. Okay. So that's why this algorithm is what's really suitable when you have millions of states in your system. Okay, so now let's actually do this. Let's generalize this almost trivially to now instead of a discrete time dynamical system, we now look at a continuous time dynamical system, right? The algorithm is exactly the same, except for instead of looking at A, you go to the e to the A. So when you look at A, it corresponds to a discrete dynamical system. And if you look at e to the A, it corresponds to a continuous dynamical system. And we can also generalize from a continuous dynamical system that's linear to a continuous dynamical system that's nonlinear, right? Again, by using a linear approximation, by initialize the system at the neighborhood of a fixed point and compute an evolving time. So let's actually show how this works for the Lorentz equation. Okay. So I think we previously already had the Lorentz implementation, so maybe let's just copy it. So what's the equivalence to this dot product? The equivalence to, so we still initialize to we still are going to initialize two random vectors, right? So we're doing the randomization the same way, but instead of 2 by 4, we have 2 by 3, right? Okay, and the equivalence to multiplying this vector by the matrix A is to actually evolve the state for a certain amount of time. Okay, so let's actually again copy this and change on top of the code. So instead of a dot product, we basically say we still take the, let me see what this, okay, so we are reshaping this to 3 and the -1, right? That means transpose is the right thing. Okay, so we are going to use OD int, let's say from scipy dot integrate for OD int Lorentz. That's the initial condition, and we are just going to evolve maybe for 1 unit time. So this is the time, and after OD int, it returns me a series of solutions at different time snapshots. I'm only going to take the last time snapshot, that's the -1, and we are going to reshape it into a matrix that's so dx dt, dy dt, dz dt, so that's 3 states, so that's 3 by, actually it's going to be 3 by 2, right? So let's just make sure we are doing the right thing. And 3 by 2, and we are doing QR factorization to the 3 by 2 matrix, so that's correct, right? Okay, and when we are also going to copy this to here, except for the initial condition doesn't have to be transpose of x0 and x1, it'll be just the q. That's our initial condition, right? So let's make sure this works. Doesn't. Oh, I need to make the initial condition one-dimensional, so Ravel would be the right thing to do, and also Ravel here. Okay, so this works, and let's just copy our previous code also to here. So, right. So on this one, for the continuous dynamical system, if we do this, we are going to get, if we do the same thing, what we are going to get is actually the exponent, I mean the exponential of the eigenvalues, right? So what we want to do is to also take the logarithm for that. We are going to copy this and paste it here. So we are going to be taking the logarithm of the whole thing, which is actually just taking the logarithm of without the power and divided by 101, right? Okay, so let's actually run this. Here is what we get, and let's actually copy our previous code. I mean, maybe we don't have to copy. We already, I think, computed. Right, we already computed the eigenvalues here, right? So actually, let's just copy that and print it anyway. We are here. So this is the real eigenvalues. This is the computed ones. Okay, so I think we are incurring the same problem as we had last time, is the nonlinearity, right? So what we have to do is we want to actually have something like epsilon equal to 10 to the minus 5, and the initial condition needs to be multiplied by epsilon, and but after we integrate the ODE, right, we want to divide it by epsilon to get the actual right. So basically we are evolving on the neighborhood, right? So we want to figure out after 1 time unit how much the solution has changed, both scaled and rotated. So basically multiply by epsilon when we feed in the initial condition, and then when we get the output, divide by epsilon is the right thing to do, right? So if, for example, if the system did not evolve, then we should get like the same as before. So again, like we want to multiply by epsilon and divide by epsilon over here. So let's actually run it again. Then we actually get roughly the right answer, right? So if we evolve it for further 1,000, let me just divide it by the length of our history. Minus infinity, that's very good. Okay, but anyway, so this one already got better, right? But this one actually became minus infinity because of underflow. So essentially, if you take the product, and the product is actually, let me actually show it. If we take the product, the product is actually too small, right? Becomes infinity. It becomes basically 0, right? So how do we fix that?
Renormalize.
Well, so look at what we are doing. We are taking the product of a bunch of numbers, right? So we are basically, the individual diagonals are actually fine. If you look at let me just copy it again. So if you just look at the array, each number in this array is actually pretty good. It's okay. The only thing that's problematic is that if you look at the second number is on the order of 0.05, right? Or 0.06. If you multiply 1,000 such numbers, you get basically the number gets too small to be represented as a double precision floating point. So the right thing to do is don't multiply them, but to take their average. So just to look at what we are doing. We are taking the product, okay? Of course, the product, the absolute value of the product is the product of the absolute value. So we can reverse this. So let me actually just do another better numerics. Okay, so let's first switch the product and the absolute value. So that's no problem. And then we are doing the logarithm of the product, right? What is the logarithm of a product? It's the sum of the logs, right? So we can also switch the log with product, except for when the product goes out of the log, it becomes a sum. So the product goes out of the log and becomes a sum. Oops. Wait, what happened? Okay, yeah, so it becomes a sum. Okay, that's okay, right? Still exactly the same thing. Now we are taking the sum of a bunch of things divided by the length of the same length, right? The length of the art history is the same length as the what is inside the sum. So the sum divided by the length becomes average, right? So we'll get rid of these and just take the mean. All right. So that is our new improved numerics. Let's see what we get. Absolute value. Okay. Absolute. I think that's the numpy's. The return array must be of array type. I think my 0 got fed into a wrong place. So I want to take the mean, yeah, so my 0 should be here. So basically x is equal to 0. So just make sure it's the right thing. Okay, so log, yeah, I think it is complaining I'm feeding the second argument 0 to some wrong function. Okay, so better numerics. The first number is exactly the same. There is right when we don't have underflow, and the second number, where is it? Yes. So now we have 3 digits of accuracy as opposed to 2. All right. Okay. Any questions on this? Yeah.
I guess the mean number is also like the sum and then divided, right? Or is like the improvement now is taking the log?
Yeah, the improvement. Yeah, so the primary improvement is taking the log before it's switching the log and the product. Yeah, so thinking about yeah, so if you first multiply, then take the log, you get the 0. You get a 0 first, right? But if you take the log, you get a bunch of finite numbers. Although the sum of them are, let's imagine the sum of the logs are like a million, right? It's still representable by double precision, but the exponential function of a million is like either infinity or 0 in double precision. Okay. Yeah. So this is actually one of the things that we almost have to be careful all the time. Is in dynamical systems, things get either to infinity or 0 really fast. So arithmetics like this, using the logarithm to represent numbers as opposed to the actual value, is actually sometimes make a large difference. Okay, so this actually leads to our next topic, is really the trade-off between round-off error and truncation error. So to really study that, let's actually look at the Lorentz system at a slightly different fixed point. So let's actually modify the Lorentz system and look at our next stage of increasing this row from 0.5, let's say, to 5. All right. So let's see what we get when we. So let's actually comment this out first, and try to start with a U0. That's random.rand 3, and U is equal to OD int Lorentz U0, and let's integrate for 10 time units, and let's plot. I think I didn't import from PyLab, import all. Let's plot the trajectory, still the x versus z plot, and see what we get. Attribute error, building function. I don't know. So what did we do before? Random.brand, somehow that worked. Did I overwrite the variable rand with something? Anyway, so let me just oh, I know, like I think PyLab also has a rand. Okay, so that I think is gonna fix this. Okay, so here is what we see is that the fixed point at 0 is no longer stable, right? So if we use a random initial condition, the trajectory is going to move away from the 0 point, and it'll spiral into somewhere here. So just from the trajectory, can you categorize what kind of fixed point this looks like? Huh? Yeah, it's a stable spiral, right? So what do you think the eigenvalues are like over here? Yeah, a complex pair with a negative real part. And what's actually this actually should have 3 eigenvalues, right? Because it's a 3 by 3 matrix. So the third eigenvalue is actually stable. That's what enables this thing to converge over that point. So the third eigenvalue is also negative. And from this equation, you can actually figure out where exactly that fixed point is, right? So, for example, the first equation, dx dt, for that to be equal to 0, x minus y minus x has to be 0, right? So x has to be equal to y. And now if you plug in x equal to y, let's see to which equation? X equal to y to the second equation. What you get is x times rho minus z minus x itself has to be equal to 0, right? So what that means is that rho minus z minus 1 has to be equal to 0. That means z has to be equal to rho minus 1, right? And rho is equal to 5 here, so z has to be equal to 4, right? Okay, so that's the second equation. Let me just write it here. So u fixed is going to be x something, y something, I don't know, but z is going to be rho. Let me just copy this over here. Z has to be equal to rho minus 1. Okay, now z is equal to rho minus 1, plug it into here. X times y has to be beta times rho minus 1, and x is equal to y. So both are equal to square root of beta times rho minus 1. Right? Actually, so that's my analytical calculation of where the fixed point has to be. So just to make sure it is actually correct, we fixed u fixed, put the big circle to make sure we get the right thing. Yeah, looks like it is there. Okay. And now an analysis to the eigenvalues also is something like this. We take epsilon, right? We take a Lorentz. Now instead of a v times epsilon, we have v times epsilon plus this u fixed. So the first dimension is x, y, z. The second dimension has to be new axis. Then let's print these. Okay, as expected, one of the eigenvalues are negative, real, and the 2 remaining eigenvalues are real, have negative real part, and is a complex pair of conjugates, right? So that is the dynamics around this fixed point when the fixed point at 0 now becomes unstable. All right. So let's actually start to compute the Jacobian, right? So this is a way of how we compute the Jacobian around that fixed point. And let's actually just print out the J itself instead of the eigenvalues. Yeah, so let's actually, we don't need that anymore, so don't. Okay, anyway, so this is the computed this is the computed eigen Jacobian, right? The derivative of the right hand side with respect to the u. So let's actually use an example to compute the directional derivative of du dt with respect to one particular direction. Let's just make it 1, 1, 1. All right, so print. So instead of a v equal to identity, we'll just say v equal to array of 1, 1, 1, and yeah, this doesn't need this anymore. So you fixed plus v times epsilon, and that is going to be the we don't need the reshape anymore, right? So this is the directional derivative computed. And let's actually take a look at the precision of this as a function of this epsilon, and see what is the best trade-off between like a numerical round-off error and the truncation error, right? So as we have seen, like when the epsilon is too large, we have yeah. So let's say when the epsilon is too large, let's say 1, we're going to have a truncation error, and when epsilon is too small, let's say 10 to the minus 16, we are going to have round-off error, right? So yeah, so we can see the truncation error becomes significant when epsilon is equal to 1, and round-off error, maybe this is too much, round-off error becomes significant, right, when epsilon is too small. So let's take a look at how this round-off error versus truncation error actually works. To do that, we actually need an analytical solution to this problem. So basically, when x, y, z are all perturbed by the same infinitesimal number, what should j analytical be? Okay, so that we can just copy this. Okay, so we can just look at it analytically.
So you're basically talking about direct tangent equation, if I remember correctly, right?
Yes.
Okay.
So j analytical is going to be equal to, let's first look at the first equation, right? When x and y are perturbed the same amount, the dx dt is going to be perturbed by 0, right? Because they cancel out. And the second equation, when x, y, z are perturbed by the same amount, it's a little bit different. So actually, let me put the derivation here because we need the u fixed. So when x is perturbed by something, dy dt is perturbed by rho minus z fixed. So u fixed 2, right? So that's what happens when x gets perturbed. When y gets perturbed, we get a minus 1, right? That's the derivative of dy dt with respect to y. And when z gets perturbed, we get a perturbation by x, which is u fixed 0. So that's the second component. Third component can be done the same way. When x perturbed, the third equation gets perturbed by u fixed 1, which is y. When y is perturbed, this gets perturbed by x, so u fixed 0. And when z is perturbed, it's get perturbed by beta, right? So these are basically the derivative of these of the 3 equations with respect to the 3 variables summed up. So that's the analytical j. And let's make it numpy array. All right. Any questions in this analytical formula? Yeah, just taking derivative. Okay, so so basically, let's compute j in this way and look at how much error we get. Okay, so as we can see that when we take a 10 to the minus 8 perturbation, we get an error that's on the order of 10 to the minus 8, right? And when we are taking an order 1 perturbation, we get an error that's order 1. And when we are taking a too small of a perturbation, we get an error that's again order 1. So let's actually not just print out these few numbers, but actually take a series of epsilons. So let's say epsilon goes to log space of 10 to the minus, let's say 16 to 0, and let's do 17 different numbers. Okay, so basically that's a bunch of different epsilons. Let's say array. Then for epsilon in epsilon array, and let's actually make another array to record the error. we are going to compute j, and instead of printing them, we say error array dot append this number. All right. Okay, and we'll just plot stuff. This time, let's actually comment out this previous plot. Yeah, let's also comment out this plot. Also don't need that. And let's plot epsilon array against the let's say absolute value of this error array. Well, so this is as we can see, this is not a very good plot because epsilon goes up by an order of magnitude every time, right? So the right way to plot this is actually to do a double log plot. And actually, let's see what this looks like. Okay, so this is one of the typical plots when you are trading off round-off versus truncation error. So that is when the epsilon, when the amount of perturbation is large, you get a increasing error as epsilon increases. And that's due to what kind of error? It's truncation, right? You're truncating the Taylor series. But when epsilon is too small, you get a rising error as epsilon decreases. That's due to round-off errors, right? Okay, and if you want to, let's just make a grid. You can see that the slope of both branches are what? What's the slope like? They're both about 1, right? So this is basically saying that when epsilon is too small, the round-off error has an order of magnitude of 1 over epsilon. And when epsilon is large, the truncation error has an order of epsilon. Okay. Now I don't know any way of improving the round-off error, but there is a way to improve the truncation error. How? Any suggestions? Higher order method, right? So what we are doing is a first order finite difference. So instead of having a first order finite difference, we can do a second order finite difference. Instead of taking just a one Lorentz evaluation, we can take a plus evaluation minus a minus evaluation, then divided by 2 times epsilon, right? So that's a central difference formula. Okay, and then let's just plot this again. Oh, bad example again. So, so you can see the Lorentz it's a quadratic function, right? Like the highest. So first of all the 3 derivatives are polynomials of the state x, y, z, and the highest order term are quadratic, like x times y and x times z, and that makes the second order formula exact. All right, so basically by having a central difference, we actually eliminated the truncation error. The result of this is only round-off error remains. If we were using a different example that's not a quadratic formula that involves, for example, sines and cosines and whatever, what we are going to see is this is going to be exactly the same, and we are going to see these kind of ends over here, and then there is going to be a slope 2 right that kind of terminates at the same point when epsilon is on the order 1. All right. So, yeah.
Slope cube rise, is the exponential the order of your numerical method? What you were saying?
Yes. Yes. The slope 2 would be the order of the central difference formula. Okay. Now, this is how we improve the round-off error. How about truncation error? Well, it turns out there is also some way of removing, at least reducing dramatically, the truncation error. So let's go back to this and do another one. But instead of perturbing in the real component, let's actually perturb in the imaginary component. Minus 1j. So basically, 1j is the imaginary number, right? So let's perturb in the imaginary axis and plot it again. Oh, minus actually divided by 1j times this. What? Sorry. Something isn't right. So why I'm getting a bunch of zeros? Oh, I made it a float 64. That's why I removed all the imaginary components. So let's actually do this again. Yeah. Okay. So what you can see is that the error is actually all the way down here, right? 10 to the minus 15. Why did I achieve that? This is because when I'm perturbing in the imaginary axis, what the computer does is it actually uses 2 double precision floating points to represent that complex number. And in all the elementary arithmetics, I mean, the Lorentz is almost the ideal case. It only involves addition, subtraction, and multiplication. But for most of simple algebra, what the computer does is it never mixes imaginary and the real numbers. So all the perturbations ended up, all the small tiny perturbations. So let's say if I have an epsilon that's equal to 10 to the minus 15. All the tiny perturbations that's on the order of 10 to the minus 15 are going to be only in the imaginary component. It never got mixed with the real component, which is the large order 1 part. So that, unless you have operations that actually mixes the real and the imaginary components, right, in perturbations, you are actually getting a much improved round-off error when the perturbation is on the imaginary axis. Okay, so these are basically some of the tricks we often use to do perturbation analysis that tries to defeat round-off error and the truncation error. So if you don't have Lorentz equation but have some more complex equations that are not quadratic, what you're going to get is, for this formula, is a second order slope line that goes all the way down and all the way and stays around the 10 to the minus 14, 15. All right. Okay, any questions? If no, let's end over here, and in the next lecture, we are going to introduce a different way of doing perturbations, the adjoint method. And if we have time, we will now start going to periodic dynamical systems away from simple fixed points. All right, so see you tomorrow.